Welcome back to another lesson on logarithms. Today we'll learn some interesting properties of logarithms that will expand our toolbox for solving exponential and logarithmic equations. Let's get started. In your guided notes for this lesson, you'll find these two equations, A and B. What do you notice? What do you wonder? Pause the video and record your thoughts in your guided notes. I notice both these equations involve only the numbers 2 and 5, but A is a quadratic equation while B is an exponential equation. I also notice that in both equations, the left and the right side have the exact same structure, and that the x has the same role on the left side as the 5 does on the right side. At first glance, it may seem obvious that the value of x is 5, but I wonder if it's actually that simple. Let's examine equation A. Is it true that if x squared equals 5 squared, x must be 5? Or is there another possibility as well? Isn't negative 5 squared also equal to 5 squared, since they're both equal to 25? Therefore, we cannot make the direct conclusion that x must be 5, because x could be something else as well. A similar situation happens with absolute value of x equals absolute value of 5. Remember, an absolute value outputs the positive version of a number. Even though the obvious conclusion seems to be x equals 5, we cannot say that for sure, because x could also be negative 5, since the absolute value of both 5 and negative 5 is 5. Now let's examine equation B. 2 to the x equals 2 to the fifth. We know 2 to the power of 5 is 32. Is there any other exponent besides 5 that would turn 2 into 32? Nope. So in this case, if 2 to the x equals 2 to the fifth, we can conclude x must in fact be 5. This example highlights an important property that exponential functions have that other functions, such as quadratic and absolute value functions, don't. We call this property the one-to-one property of exponential functions. You might remember the term one-to-one from when you studied inverse functions in Unit 1. You learned that a function is one-to-one if no two different inputs produce the same output, which is exactly what we're saying here. This is opposed to, for instance, the quadratic function x squared, where there do exist different inputs that produce the same output. For that reason, quadratic functions are not one-to-one. But in the case of the function 2 to the x, not only is the output 2 to the fifth produced exclusively by the input 5, but every output of 2 to the x corresponds to only one input, which is why we consider it one-to-one. We generalize this one-to-one property by saying that b to the x equals b to the y if and only if x equals y. We just applied this property with the equation 2 to the x equals 2 to the fifth. Thanks to this property, we can automatically conclude x equals 5. In other words, this property assures us that if two powers of the same base are equal, their exponents must be equal as well. Let's apply this property to solve some exponential equations. Here's the exponential equation 7 to the x plus 5 equals 49, which you'll also find in your guided notes. How can the one-to-one property help us solve an equation like this? Well, if we had the powers of the same base on each side, the property would allow us to set the exponents equal to each other. Having this in mind, pause the video and try to solve this equation yourself. We know 49 is a nice power of 7. If we rewrite the 49 as 7 squared, then, by the one-to-one property, x plus 5 must equal 2. Then we just subtract 5 on both sides and get that x equals -3. Notice the key here was getting the equation to the form b to the x equals b to the y, so that we could then set the exponents equal to each other and isolate x. In this equation, the choice of base was pretty straightforward, but that's not always the case. Let's try one that looks a bit more complex. 1/8 to the 5 minus x equals 4 to the 7x minus 24. 1/8 is not a very recognizable power of 4, and let's not even try writing 4 as a power of 1/8. What do you think we can do here to make the bases the same? Instead of trying to write the 1/8 as a power of 4, or vice versa, why don't we rewrite both numbers as powers of a smaller, simpler base? Pause the video and try to use that idea to solve this equation yourself. One-eighth and 4 are both powers of 2, so we can rewrite 1/8 as 2 to the -3 and 4 as 2 squared. We can then simplify by multiplying the exponents. -3 times 5 minus x is -15 plus 3x, and 2 times 7x minus 24 is 14x minus 48. Since we have equal bases, we apply the one-to-one property and set the exponents equal to each other. Now we just solve for x. Let's subtract 3x and add 48 on both sides. We get 33 equals 11x. Finally, we divide both sides by 3 and get that x equals 3. Let's do one last exponential equation. 3 to the 2x minus 11 minus 2 equals 5. How would you start solving this one? We first need to take care of the fact that it's not in the correct form to apply the property. We need a single term on each side of the equation, but on the left side we have a -2. We can address that by adding 2 on both sides, and we get 3 to the 2x minus 11 equals 7. Now we need to find a way to have the same base on both sides. Any ideas here? 7 is not a recognizable power of 3, and I can't think of a smaller base that would work nicely for both either. So what do we do? If only there were a way to turn that 7 into a power of 3. Wait, there is! We can just write it as 3 to the power of log base 3 of 7. Now we just apply the one-to-one property and get 2x minus 11 equals log base 3 of 7. We add 11 on both sides and then divide both sides by 2. The solution is x equals log base 3 of 7 plus 11 all over 2. The one-to-one property of exponential functions has turned out to be really helpful in solving exponential equations. In the first two equations, we were able to avoid logarithms altogether because of it. But even if logarithms are needed, like in this example, this property will always work. Thankfully, logarithmic functions have this useful property as well. The one-to-one property of logarithmic functions says that log base b of x equals log base b of y if and only if x equals y. This property assures us that if two logarithms of the same base are equal, their arguments must be equal as well. Why does this make sense? Consider the equation log base 3 of x equals log base 3 of 9. Remember, this statement is equivalent to saying that 3 to the power of log base 3 of 9 equals x. Furthermore, by definition of a logarithm, we know 3 to the log base 3 of 9 must equal 9. And just like that, we showed that if log base 3 of 9 equals log base 3 of x, it is automatically true that x equals 9. Let's put this property to work. Let's solve the logarithmic equation log base 6 of 9x minus 10 equals 3 log base 6 of 2. How is this equation different from the other log equations we've solved? This time we have logarithms on both sides. Thankfully, these logs have the same base, so we could potentially use the one-to-one property to simply set the arguments equal to each other. But for us to be able to do that, the equation would need to be in the form log base b of x equals log base b of y. Our equation would look exactly like that if it weren't for that 3 in front of the log base 6 of 2. What do you think we can do about it? We can use the power property. We just bring up the 3 as an exponent of the 2, and we end up with log base 6 of 8 on the right side. Pause the video now and try to use the property to solve the equation yourself. By the one-to-one property of logarithmic functions, we conclude that 9x minus 10 must equal 8. We then isolate x by adding 10 on both sides, and then dividing by 9, which gives a solution of x equals 2. To wrap up our lesson, let's apply the property to solve one last equation. ln of 1 plus 4x minus ln 8 equals ln of 2 minus x. Pause the video and give it a shot. Once again, before using the one-to-one property, we need the equation in the form log base b of x equals log base b of y. We can achieve this if we combine the logarithms on the left side with the quotient property by dividing the arguments. Then we can apply the one-to-one property and get that 1 plus 4x over 8 equals 2 minus x. Lastly, we isolate x by multiplying both sides by 8. Adding 8x and subtracting 1 on both sides, and dividing both sides by 12. We get that x equals 5 over 4. In this lesson, we learned two important properties that allowed us to solve a wider range of exponential and logarithmic equations: the one-to-one property of exponential functions and the one-to-one property of logarithmic functions. In our next lesson, we'll wrap up the last 3 lessons by reviewing all the strategies we've learned to solve exponential and logarithmic equations. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time! Hey.